Hello. So I'm here to present the paper Function Private Conditional Disclosure of Secrets and Multi-Evaluation Threshold Distributed Point Functions. I'm Nolan Miranda, and I worked with Fuyi Yo and Vipin Singh Sehrawat on this paper, and I'm very happy to tell you all about it. So let's go into first the definition of function secret sharing, which is the core problem of this paper. So it's a special case of something called secret sharing, and specifically it's for functions. So a dealer is going to split a function f in a family of functions, big F, and this is going to be split into shares, f1, f2, and so on, up to fn, and distributes these to the parties p1, p2 through pn. F of x now can be reconstructed from an authorized subset of these fi's. So when you get a certain number of parties together that have these function shares, they get the input and they compute their shares and they bring them to reconstruction. And from reconstruction, we can figure out the actual output of the function on the input x. So the whole point of function secret sharing is that this time the parties learn nothing about the choice of f. F is the secret here, not the input, but the actual function. And so these authorized subsets of parties that you can figure out the actual function output for lie in this access structure called gamma. And so the access structure just specifies which sets of parties are allowed to reconstruct the output. And we have two general notions that are very common here. We have the threshold access structure, where if the sets are of size t or greater than threshold t, then the parties can reconstruct the output, but any set of less than size t cannot reconstruct the output. So all sets of size t or greater are in gamma. And the general access structure is you can specify any arbitrary collection of subsets of parties. You can make it just p1 and p5, you can make it p1, p2, p3, p4, you can specify any collection of subsets of parties, and that is a general access structure. So we were able to achieve function secret sharing for two classes of functions in our paper. And so I'm going to first start with the first class, and this class depends on a concept called Conditional Disclosure of Secrets, or CDS. This was first introduced in a paper by Gertner et al. In 1998. So the gist of this concept is that there are n parties and they all have some input, and they generate messages, and they're going to send these to an external third party named Carol. And if a particular Boolean condition function h on the input y is met, i.e. if h of y equals 1, then Carol gets to learn the secret s. Otherwise, she learns nothing about the secret if h of y equals 0. And so this is the conditional disclosure of a specific secret. So pictorially, what's going on here, we start on the left with input y, and for this example, we're going to assume that h of y equals 1, that the Boolean condition function has been met. Then the n parties receive this input. They all generate some message, m1, m2, m3, and so on, some individual message. They don't collaborate with each other, only generate the message themselves, and they all send a message to Carol, who receives these messages and then runs some sort of algorithm, some reconstruction algorithm, let's say. And she runs it on m1, m2, m3, and so on, and she outputs s. And the point is that Carol will only get the correct s if h of y equals 1. Basically, the party's behavior is based on this input. And if h of y equals 0, Carol will output the wrong secret or reject, depending on how you define it. So in order to turn this into a function secret sharing scheme, we needed to make some additional assumptions. And so we introduced a new version of CDS called Functionprivate CDS, FP-CDS. And in this, we introduced a dealer, and this dealer is going to generate shares WJ. Now, these shares aren't exactly the input, they're a part of the input, but the parties, the PJ, actually also get a choice of part of the input. And so they get to generate a message, but their input is not only the WJ from the dealer, but a CJ. And the CJ is a portion of a condition. And this is like the y, a portion of the y that PJ gets to choose. So there's both the part of the dealer and the part that the PJ gets to choose. Well, these messages are sent to Carol as usual. And Carol is going to output the correct secret if and only if the Boolean condition function h outputs 1 on all of the CJ. And so h now is not only taking in one input, it's taking in one input per party. So it's the cross product of many sets in which all of these condition portions lie, C1 cross C2 cross C3 and so on. Now, the point of function private CDS is that actually the condition function remains private for the parties based on the assumptions we've made. And Also, the condition portions of other parties aren't made public to the parties themselves. So party 1 is not going to know what C2 is because that's the portion that party 2 chose, for example. And these assumptions are very key for us to reduce this into a function secret sharing scheme, as we'll see in a bit. But of course, it is good to check that there is such a scheme that exists at all. And so we were able to derive a scheme, and it shows that this class does have some functions in it. And we give an example of this in our paper. OK, now how do we get from FPCDS to FSS? What's this reduction look like? Well, the key insight here is that Carol is really just an algorithm that can be run by the party themselves. They can just take their messages, publish them, and then simulate the Carol algorithm and see what the output is. And so the nice thing about this is that the function privacy and the condition portion privacy we just talked about on the previous slide from the FPCDS scheme, they make sure that the function, the condition function, is actually remaining secret. So what are we actually sharing here? Well, we're trying to see the output of the Carol function and deduce something about the inputs. So that means that we're actually sharing the condition function. We know that if Carol outputs the secret, the condition function's output must have been 1. If Carol outputs reject or the wrong secret, we know that with very high probability the condition function's output must have been 0. And so what does this look like? The dealer is going to pick the WJ just like the dealer for the FPCDS scheme, and is going to deal these to all the parties. Now the parties at the FSS scheme are just going to basically act like the parties for the FPCDS scheme. It's the exact same thing. But the reconstruction shares of the FSS scheme are the messages, the MJ from the FPCDS scheme. Each party is going to generate their own message. But the reconstruction process is actually the Carol algorithm. As I mentioned before, we're going to publish all of these messages, run Carol on them, and see what the output is. And if Carol rejects, we're going to output 0 because h of y must have been 0, where y is this sort of chain of condition functions, basically, or condition portions, sorry. And if Carol doesn't reject or outputs the secret, we can output 1 because we know that the condition must have been met. And so this way, we actually are sharing a family of Boolean condition functions. So let's talk about the second class of functions that we were able to share. And this class of functions is called point functions. And these are functions where p sub a b of x is equal to b when you plug in x equals a and 0 elsewhere. And distributed point functions is just a way of saying function secret sharing for point functions. So point functions are just points where, or functions where there's only one point that's non-zero, and that's when you plug in x equals a. So threshold function secret sharing already exists for point functions, but we are able to present a new scheme in this paper that allows for multiple evaluations without leaking information. And the way we're able to achieve this is using key homomorphic pseudorandom functions. I do want to make one small point. When the scheme is run on x equals a, it's unavoidable actually to leak the function because the input is public to all the parties in FSS, and the output b, when you get a non-zero result, you certainly learn that you have plugged in a. And so it's impossible for an FSS scheme not to leak any information when x equals a is the input. But aside from that, we are able to mask when x is not equal to a, the information about a and b. And so the way we're able to achieve this is using KHPRFs. Now let's quickly talk about what those are. A family of pseudorandom functions is key homomorphic if given f sub k1 of x and f sub k2 of x, these pseudorandom functions that are parameterized by keys k1 and k2 respectively. There is an efficient algorithm to compute f sub k1 XOR k2 or f sub k1 plus k2 of x. And so basically, given two pseudorandom functions in this family, we can combine their results to get as if we had evaluated with the sum of the keys instead, efficiently. So Beimel et al. In 2000 introduced a DPF sharing scheme that was not leak-proof for multiple evaluations, but led to an interesting improvement in our paper. And the high-level idea is that the input x of p sub ab, we can test each bit of the input if we just take two vectors for each bit, one for when the bit is 0 and one for when the bit is 1, and then sum across the appropriate vectors. So for 1, 0, 1, for example, you'd take the vector for bit 1, the vector for bit 0, and the vector for bit 1 for the first, second, and third indices of the input. So formally what this looks like is if we say the input has length L, we're going to generate two L vectors, v0, v1 through v2L minus 1. And actually, v sub 2j plus aj, where aj is the jth bit of the input, if we take the sum across all those, it's pretty random looking. And so what does the sum actually mean? The sum just means for the jth bit of the input, we take v2j or v2j plus 1 if the jth bit is 0 or 1. So for the aj, which is the correct input that yields b for PAB, we take the 0th vector or the first vector if the first bit is 0 or 1, then the second vector or the third vector if the second bit is 0 or 1, and so on. Now, for each of the vk's from v0 to v2l minus 1, we can take a share and distribute v sub ik to party pi. And so each party gets a share of each of the vectors. Then for some input x, maybe not equal to a, maybe equal to a, the parties on a high level are able to reconstruct the sum of v sub 2j plus xj, which is the sum across the appropriate vectors for the bits of their input x, and check, is this sum equal to the sum of the actual v2j plus aj, the right input? And then if it is, they know that they have plugged in x equals a, and if they haven't, then the output is going to be essentially random looking. So how does our scheme work? The dealer is going to distribute for the point function p sub a comma alpha of x. Remember that this is the function where you plug in x equals a and you get output alpha. We're going to distribute, just as before, the additive shares of 2L random vectors that were taken for each bit of the input of a or x. And so these v0, v1 through v2l minus 1, we sample these random vectors and then we give additive shares. And we're going to take the sum across the appropriate vectors for each bit of the input. So for the jth bit of the input, we add v sub 2j plus a sub j, where a sub j is the jth bit of a. And remember, this is the correct input, or the input that yields alpha. And we also generate 2L random vectors for each bit of the input of alpha, or sorry, not input, but the output of alpha. So we're actually going to generate additive shares for 2L random vectors alpha 1, alpha 2 through alpha sub 2L minus 1. And we're also going to generate 2L key homomorphic pseudorandom function keys, ki0, ki1 through ki2L minus 1, also corresponding to the bits of the input, for each party pi. And so there's a total of 2L times n keys. And then we're going to generate one big key, and this big key is going to be the sum over appropriate KHPRF keys. And what this is for each party's keys, we take the sum of the keys that correspond to the correct bits of the a, the important input to p sub a comma alpha, and then we add up actually all of those results, and that gives us k, this big kind of sum of keys. So now that the share generation is out of the way, let's see how we evaluate and reconstruct. So when parties receive their shares, they're going to compute two things. They're going to compute s sub I comma 0, which is the sum over the appropriate bits of the input x for their vector shares. And they're also going to take the pseudorandom function evaluated on the key according to the keys according to their appropriate k sub I 2j plus xj. Remember that these are both indexed by the bit of the input that they get. So if the first bit is 1, they're going to use a certain vector for that. If the second bit is 0, they're going to use a certain vector for that. And then for the keys, if the first bit is a 1, they're going to use a certain key for that. And if the second bit is a 0, they're going to use a certain key for that. And they're going to take the sum over those results, and they're going to take another sum over the alphas. So the same thing, but they're going to plug in the alpha I and the ki to another pseudorandom function. And they're both going to use the pseudorandom function with a seed r. Now, what happens when they do this? Well, if the first sum, if they take the sum, if all the parties come together and add together their first sums, then this is going to be theta plus f sub 1 k comma r. And this is only when x is equal to a. And the intuition is that the first thing in that si comma 0 is going to add up to theta, because that's the correct sum over the bits of a. And the second thing in si comma 0, because of the key homomorphic pseudorandom function nature, this is going to combine into f1 kr. So if these two things are equal, the sum over the first sums and theta plus f1 kr, then it must be the case that the input x has been a. So we can output alpha. And what is alpha going to be? Well, alpha is only going to be correct if si comma 1 comes out to the actual alpha plus f sub 2 kr. And so the gist of it is that in the second sum, si comma 1, the first part of that sum is going to sum to the alpha if xj equals aj for all j. And then the second part of that sum, f2 of the ki's, is going to be f2 kr if xj's correspond to the aj's again. And so alpha must be the difference between the second sum and f2 k sub r. So then we're just left with alpha. Otherwise, if we get anything else, then with very high probability, x was not equal to a. And so our output is actually going to be 0. And so this works with very high probability. So this was a lot of dense notation. So let's just go over the intuition of why it works. So when x is not equal to a with key-homomorphic PRFs, we don't actually leak any input or output information. And the intuition is that without the KHPRF, we're doing some linear operations on these vectors that correspond to the actual input a. And so somehow this is probably going to leak information about a unless we use the PRF output. And the PRF output provides a pseudo-random mask for our reconstruction process. And so parties don't learn the information. The key homomorphism actually allows for parties to compute individually, and then we can combine the results later. If we weren't able to do that, then there would be no way to make sure that the masks cancel out in some sense. The previous slide showed an n out of n case, which required all parties. So the access structure was actually only the set of all parties. But this can be extended to the threshold case just by using Shamir shares for all the vectors and then choosing the keys based on a certain polynomial interpolation scheme. And we have more details in our paper. So just to recap, what have we gone through? We learned about function secret sharing, which just splits a function f into shares fi so that parties can evaluate a function without knowing what the actual function is. And then we talked about FPCDS, function private conditional disclosure of secrets, which allows for construction of an FSS scheme for Boolean condition functions by a reduction from CDS to FPCDS, and FPCDS, a specific subset of CDS that can be reduced to FSS. And then multi-evaluation threshold distributed point functions, which is the thing we just talked about, allows for repeated evaluations for DPFs or FSS schemes for point functions. And this was achieved using KHPRFs to basically provide a pseudorandom mask. So I'd like to thank y'all for watching this. And I'd like to thank my mentors at Seagate and my mentors at Stanford for helping me. And I had a lot of fun with this project. So thanks for watching.